In this section, we will study some basic facts about convex functions in Rn. Now, let us denote by R bar the extended real line where the infinity value is allowed. Okay, and here we use the following rules of arithmetic calculations. If we have a real number alpha, then alpha plus infinity is equal to infinity plus alpha and is equal to infinity for any real number alpha. The second rule is alpha times infinity is equal to infinity times alpha and is equal to infinity for any alpha greater than 0. Okay, and then we also use the rule that alpha infinity plus infinity is infinity and infinity times infinity is also infinity. Another important convention is that 0 times infinity is equal to infinity times 0 and is equal to 0. Okay? So now we're going to talk about convex functions with extended real values. So this is definition 1.32 from the textbook. Okay, now let omega be a convex subset of Rn. An extended real value function f from omega to the extended real line is called convex if the following property is satisfied. If f of lambda x plus 1 minus lambda y is less than or equal to lambda times f of x plus 1 minus lambda f of y. This is true for all x and y in omega and lambda in the interval 0, 1. Now, if the inequality above becomes strict whenever x is different from y, we say that f is strictly convex. Now I'm going to explain the convexity of functions using geometric interpretation. So now this is the graph of a convex function. Here, if we have 2 points x and y in the domain of the function, then then we draw the line segment connecting 2 points x f of x and y f of y. Then the graph of the secant line connecting x f of x and y f of y always lies above the graph of the function within the interval xy. Okay. Next, I'm going to talk about some important concepts that will be important in what follows. This is definition 1.33 from the textbook. In this definition, I'm going to talk about the domain and the epigraph of an extended real-valued function. Now, let f from Rn to the extended real line be a function, actually extended real value function. Then the domain of f is given by so the domain of f contains all x in Rn such that f of x is less than infinity. Okay, and the epigraph of f is given by epi of f contains all order pair x lambda where x is in Rn, lambda is in R. Note that here lambda is a real number. It's not an extended real value number, but it's a real number. And here lambda is greater than or equal to f of x. Okay? So in order to understand these concepts, I'm going to give a simple example. Here, we consider the following function. Consider the function f of x given by f of x is 0 if the absolute value of x is less than or equal to 1, and infinity if the absolute value of x is strictly greater than 1. Here x is in R. Okay? So here we can easily see that the domain of f is the closed interval -1, 1. Okay? Because f has finite values on this interval, and f of x is equal to infinity if x is not in this interval. And we can also see that this is the epigraph of the function f. Okay, and it is actually minus 1, 1 times 0 to infinity. Now I'm going to talk about some important remarks. Now let f from Rn to the extended real line be an extended real value function. Then we have the following conclusion. Now, if f is a convex function, then the domain of f is a convex subset of Rn. Okay. Now, the proof of this property is very simple. So I'm going to explain it over here. So let omega be the domain of the function f, and this is a subset of Rn. So we're going to show that omega is a convex set. In order to do so, we fix any x and y in omega and any number lambda in the interval 0, 1. By the definition of the domain of f, we have the following. F of x is a real number, so we can say f of x is less than infinity, and also f of y is less than infinity. Okay. Because f is convex, we have the following. F of lambda x plus 1 minus lambda y is less than or equal to lambda times f of x plus 1 minus lambda times f of y. Note that f of x here is a real number, f of y is a real number, therefore this is a real number. Thus, lambda x plus 1 minus lambda y belongs to the domain of the function f, which is omega. So we have proved that if x and y are in omega and lambda is in the open interval 0, 1, then lambda x plus 1 minus lambda y belongs to omega. Therefore, by the definition of convexity of sets, omega here is a convex set.